This presentation will discuss how to solve oxidation reduction reactions and to balance them using the half reaction method. The first thing that we need to do in this process is to assign oxidation numbers. This means to decide what the charge of an atom in a particular compound is. There are some rules that we follow to do this, and so we'll list those out before we get started. The first rule is that any atom in its elemental form, like hydrogen, will have an oxidation number of 0. It has no extra electrons or no lost electrons. Any monatomic ions, like sodium positive single atoms, will carry the charge that they're written with. Nonmetals will generally have negative charges, though in some cases there will be exceptions to this. Oxygen is generally -2 when ionic and molecular compounds, except for peroxides, where it has a -1 charge. Hydrogen is generally +1 when bound to nonmetals, and -1 in hydrides when it's bound to metals. Fluorine is -1 in all compounds. The other halogens are usually also -1, but they can vary. Specifically in oxyanions, they can be positive. Things like ClO, hypochlorite, they'll be positive to offset the negative oxygen. The sum of all oxidation numbers in a neutral compound has to be 0, and the sum in any kind of ion must be equal to the charge of that polyatomic ion. For example, in SO2, oxygen is -2, so to keep the compound neutral, S must be +4. In ClO3, the oxygen is still -2, so the chlorine must be +5 so that the 3 oxygens and it combined still keep a -1 charge. Some other examples: we're going to find the oxidation number of iodine in hypoiodite and in periodite. So in hypoiodite we have an iodine and an oxygen, and we want to apply the rules that we saw before. We know that oxygen is always -2 unless it's in a peroxide or bound to a fluorine. Well, in this case it's not in either, so we're going to assign it a charge of -2. There is 1 oxygen carrying that -2 charge. It must be added to 1 iodine carrying some charge. If we solve through and see, this must equal the -1 charge of the ion. So if we solve for x with simple algebra, we see that the charge on iodine must be +1. Following the same thought process, in IO4 we now have 4 oxygens, but we still have to maintain a negative charge. So my -2 is now happening 4 times from the 4 oxygens. There's still 1 iodine that must be combining with that to produce a -1 charge. And again, simple algebra will tell me that the charge on iodine in this compound is +7. Some basic ideas before we begin looking at reactions is that oxidation is going to occur when atoms lose electrons. If you want to think of this in mnemonic form, you can think of oxidation is loss, or OIL. The flip side of that is that reduction occurs when atoms gain electrons, so reduction is gain, or RIG. And so if we need help remembering this, we can think of the mnemonic oil rig. Oxidation is loss, reduction is gain. So if you get stuck, refer back to that. It's also important to note that oxidation and reduction don't happen independent of each other. The electrons have to have somewhere to go, and they have to come from somewhere. And so these two things generally happen in tandem, though they can be in separate chambers and forced through a connecting wire, like a battery. This is okay, but they have to have somewhere to come from and somewhere to go. Okay, so these redox reactions, or oxidation reduction reactions, are balanced using what's called the half reaction method. And that method has a series of rules as well that we'll lay out before we apply it. So the first thing we need to do is assign oxidation numbers so that we see who's changing in a positive way, who's being oxidized, and who's changing in a negative way, who's being reduced. So that once we get that, we're going to split this into 2 reactions. We're going to focus specifically on the species that's being oxidized in the oxidation half reaction, and specifically on the species that's being reduced in the reduction half reaction. Then we're going to balance each half reaction using the following guides. And we're going to do this like we're doing it in acid solution. You'll find later that we always do everything in acid solution and then make adjustments if we happen to be working in a base. First thing I want to do is balance all elements other than H and O. H and O can be taken care of with water since we're in an aqueous solution, so it's important that we get all other atoms taken care of first. Then we'll balance oxygen by adding H2O to the side that needs more oxygens. To counteract the hydrogens we just added, we'll balance the H's by adding H plus or hydronium to the side opposite the water. Then we have to add enough electrons as reactants in the reduction half reaction so that we reduce the charge to the proper level. And then also in the oxidation half reaction we need to make as products electrons so that we are giving off the right number so that my charge rises to the right positive level. And then if these two numbers are not the same, if I'm losing more electrons than I'm gaining or vice versa, then we have to multiply each half reaction by an integer so that we have the same amount of electrons being lost in one reaction as are being gained in another. And then step 4 is to add those two reactions together algebraically, which means we cancel out any species that appear on both sides of the reaction. And last but not least, we check for both mass and charge balance to ensure that we've done the process properly. So something I want to make very clear to you is that this is very, very common on the AP exam. It shows up in the reaction section. It's almost guaranteed to show up in an electrochem question on the open response. So it is in your best interest to know this. Know this, know this, know this. Don't ignore it. Alright, so we're going to work a quick example in acid conditions. We're going to look at dichromate reacting with chloride to produce chromium-3 and chlorine gas. So the first thing that we're supposed to do is split into half reactions, and before we can do that we would need to assign oxidation numbers and see who's changing where. Well, if we look at dichromate and follow what we did on the slides where we were talking about iodate and periodate, or hypoiodite, and periodate, we would see that chromium starts off as +6 in the dichromate, ends up as +3 over on the product side. And so this looks like a reduction. Charge is dropping. If we look at the same thing with chloride, we're going from Cl- to Cl0 because elemental chlorine has a charge of 0. And so this is oxidation. Charge is becoming more positive. So we'll write these down. There's my oxidation half reaction. There's my reduction half reaction, just like we verbalized. Now we're going to balance them using the previously described method. So I'm going to rewrite them here, starting with chloride. And the first thing that we're to do is to balance the elements that are not oxygen or hydrogen. So in the first reaction, I have 2 chlorines on one side and 1 on the other. So I'm going to add a 2 there, so that now I have the same number of chlorines on each side. Down at the bottom, we're going to look where we have 2 chromiums in the reactants, but only 1 in the products. So we'll fix that also with a coefficient of 2. Next, we're to handle oxygens by adding water. Well, the first reaction, the oxidation reaction, has nothing but chlorine, so we'll come back to it in a minute. But it looks like I have 7 oxygens in the dichromate and none on the product side, so we're going to add 7 waters to the product side to take care of that. Now I've just introduced 14 hydrogens from these 7 waters, and so I have to counterbalance that with the free-floating acid on the other side. So 14 hydroniums will go to the other side, and that takes care of all the atoms that are present. Now, in order to balance the charge and to make sure that we actually have electrons available to do oxidation and reduction, we need to go back to the oxidation reaction and see that each of these is going to give up 1 electron when it goes from Cl- to Cl0, and since there are 2 of them, it's happening twice. 2 electrons are expelled from the oxidation reaction. If we look down at the chromiums, each chromium is going from 6 to 3 as we established earlier, so that's 3 electrons per chromium. So the reaction is going to require 6 total electrons to be consumed. And so now we have each half reaction balanced by charge and mass. Step number 3 is to multiply those half reactions so that we can balance lost and gained electrons. The oxidation reaction is losing 2, while the reduction reaction requires 6. These are not equivalent. The least common multiple of 2 and 6 is 6, and so we will then work to produce 6 electrons in the oxidation reaction. So if we multiply the oxidation reaction by 3, and keep the reduction reaction, the same by multiplying by 1, we should produce the same amount of electrons in the oxidation reaction as we consume in the reduction reaction. So now we'll add them together, seeing that my 6 electrons now cancel out. All other species remain intact. So we rewrite all reactants, all products added together, and there you have the acid condition oxidation reduction reaction between dichromate and chloride. If we are to move this into base conditions, the only thing we're going to change is what we do at the end. Steps 1 through 5 are identical. All we're going to do is rewrite that since we've already done it on the previous slide. The change is that we're in base and there's no H plus around. So in order to take care of that, we just think logically, what would happen if I had H plus produced or used in the presence of a base? They would combine. So in order to take care of that, we'll add enough hydroxide to both sides to consume all of our H plus. And so one side it will get converted to water, on the other side it will remain hydroxide, and then we'll cancel out the excess waters that happen as a result. So if I take that reaction, looks like I've got 14 H pluses, so I'm going to add 14 hydroxides to each side. On the reactant side, those 14 OHs are going to combine with the 14 H pluses to make 14 waters. They'll maintain as 14 hydroxides on the product side. If I rewrite that, or combine those, and cancel out like terms, 7 of my waters will cancel out with the 14 on the reactant side, leaving me with 7 H2Os as a reactant and 14 OH minuses as a product. So this is what the reaction looks like if it happens in base. Note the difference. The waters have moved from the product side to the reactant side, and the H plus has been eliminated and replaced with OH minus as a product.